Okay, welcome. My name is Javier Garcia. I come from Spain. And today I am going to tell you about the high-level open-free FPGA development tools from Open Hardware Repository. First, in order to advance, this is an outline of the things, of the topics I want to introduce you today. First, we are going to see something about Open Hardware Repository and FPGA. Then I am going to introduce you the SDL make tool. It's the core ingredient of all the things I want to introduce you today. Then we speak about the Libre FDA tool. It's an HDL filter design and analysis tool. And then we will move to some more advanced concept that I want to introduce you. So let's move on. And first, what I want to tell you about the Open Hardware Repository. I don't know if you know it, but from its own definition, the Open Hardware Repository is a place on the web for electronic designers at experimental physics facilities to work in, to collaborate in open hardware designs. It was started and maintained by CERN, and today there is a global effort in which multiple companies and universities collaborate in different projects. This is much in the philosophy of the free software movement, and this, of course, is not only for experimental physics. You have a lot of useful resources that you can reuse for other kind of projects. In the Open Hardware Repository, FPGAs are a must because there are so many reasons because FPGA technology is employed in experimental physics facilities. First, you need a string timing accuracy and performance requirements. You need to go to the bit level. The lower volumes of the system that are being deployed doesn't justify a custom ASIC development, and you need to be you need enough flexibility and reconfiguration capabilities in order to evolve with the experiments itself. Now we can go to the first tool, maybe the most important one, and it's HDL make. The main purpose of HDL make is to be a command line Python application that is targeted to make the life easier for the HDL developers. What does it mean? First, that is very focused to have a very modular design so that it allows the agile management and reuse of HDL cores. So you can define the whole design hierarchy by using very simple Python manifest.py files. And it, in addition, supports both local and remote models that you can have in your own computer or use Subversion or Git repositories. In addition, it has a lot of useful resources for the command line. It provides a set of functionalities that are targeted to scripting so that you can create projects and update those projects for different FPGA synthesis tools. It also is able to generate makefiles for synthesis and simulation. And it has many other features such as code fetching and remote synthesis that makes the life easier to work with HDL. About the supported environments, with respect to synthesis, nowadays it supports Xilinx with all the different synthesis tools that Xilinx has. It also supports Altera with the Quartus 2. It also supports Microsemi with the Libero IDE environment, and also supports for Lattice. About simulation, it supports both proprietary tools such as iSim, ModelSim, Active HDL, even Riviera is a work in progress. And also, it supports free open tools such as GSDL or Icarus Verilog that you have you have just discovered or heard about. And about operating system, it can run in any Linux distribution that is that has Python 2.7, and it can also be used in any Windows distribution by just using a thick WinCell. Now, as we can see that all the different synthesis tools that we can use, if we take a look to the market set by vendor in the fourth quarter of 2014, HDL make tool is able to cover roughly the 99% of all the FPGA market share nowadays. So it's a very interesting tool. Now, I'm going to show you some example in order to take a feeling of this tool. So here I have the code of HDL make that I have downloaded to my computer from the Git repository that is hosted at the Open Hardware repository. And if we take a look, we have different folders. This is the code that just download from the repository. We take a look to docs. We have a lot of Sphinx documentation that is also hosted in the Read the Docs repository. If we take a look to HDL make, we have all the Python code. And it's very interesting that we have some tests that are already ready for start to work with the HDL make. So as a simple example, we can go to this test, the counter test. And here we have a full project that you can reuse in order to synthesize code like a simple counter and simulate the counter in all the different tools that I have just introduced you. So, for example, we are going to run a simulation. Just go to simulation. We have examples for all the tools that I have introduced you. And if we go to Verilog, called Verilog, we have a very simple manifest. This is describing the top file of the system. I'm sorry if you cannot see it so well. Oof. Yes, maybe, but here I'm going to run out of time. What? Cat? Ah, okay, sorry. Yes, yeah. It's a very simple one. As you see, you have a very simple line. I don't know if you can see it. It's a very simple one. You know, they have specify the top module. It also includes a post-synthesis command that you can include in order to make the thing even easier. And it describes the module hierarchy. Now, if we run HDL make, we can see that automatically a make file has been created. And if we take a look to this make file, it's a standard make file that has all the targets, and including the target with this post simulation command. So now if we run just make sim post cmd, it automatically runs the simulation. It opens the model that is going to be inspected. And we can just append this. And we have all the counters. It's just a simple example that you can use to build a more complex one. Now, we continue with the tools I want to introduce you. We have the Libre FDA tool. The Libre FDA tool is an under-development tool that is meant to be a free open Python software package aiming to help the analysis and design of HDL filters. It's basically the main purpose is to try to reduce the non-recurrent engineering. So coding an HDL filter might be is a very straightforward but time-consuming task. And having an automated tool for this it increased the productivity by very much. The idea is that we have a lack of alternatives, of open alternatives, but we have other products like the FDA tool, the commercial package that is included into MATLAB, and we are going to try to replace this tool. So if we take a look to the MATLAB ecosystem, the FDA tool needs an extra package, some extra MATLAB package in order to run. And in this way, the Libre FDA tool also needs an extra Python environment in order to run. It relies in scientific Python package, so NumPy for numeric simulation, SciPy for signal processing libraries and so on, and matplotlib in order to plot the graphs itself. It has very nice features. The first set of them matches the commercial tools alternatives, such as a friendly graphical user interface. In our case, it's based in Qt. It supports for BSDL and Verilog code generation, including its associated test benches. It includes multiple high-level filter realization resides, and it supports LTI coefficient analysis in both frequency and complex plane domains. But what, pardon? Linear with time invariant. Yeah, sorry. As an extra bonus, we have also integrated a simulation engine. So by using HDLMake that I have just introduced you, virtually any simulation tool in the market can be employed to simulate the filter that you are going to create. Okay. Now let's see LibreFDA tool in action. We have a very simple interface within which we can define a stimulus. We have chip signal. We can change to sawtooth, to scene1. And if we came back to chirp, for a simple example, we are going to change the frequency in natural units. And we see that the stimulus get the update. Now, if we go to the filter side, we can specify some different recipes for the filter, and we can see the associated transfer function. For example, if we can change the number of coefficients, the width of the coefficients that are going to be used, and the input and output boost. And we can also, and that in the filter parameters, we can see that the function transfer is changed. We can also choose different windows in order to run to implement the filter itself. And now that we have, if we change also the cut frequency, we see that it automatically simulates everything. It plots the signal, and we can make a focus and see that there is different for the flow out and for the HDL implementation. Now, finally, I know that I am running out of time. I wanted to introduce you one more concept. I am going to move faster. I want to introduce you the spec before introducing you the concept I want to talk about. This is the simple PCI Express carrier, FPGA mezzanine carrier. That is a development by the third. It's fully open hardware, and it's released under the third open hardware license. And it supports multiple functionalities by adding different FMC modules. What we need to run a whole a product based on the spec. We need different building blocks. For example, we need the hardware, that is the spec board itself, and a host computer. We also need the gateway. In the open hardware repository, we have different feature-specific gateway designs that can be loaded on the fly in the FPGA that is in the spec board. And we have also a software support that includes both the Linux user library and the kernel drivers. But there is still a piece that is missing. We need also a customized Linux operating system image in order to run the whole product as a whole, as a self-contained one. So I have made some experiment in order to build a customized Linux image, and I have chosen to use the Yocto project one. Yocto project is an open source collaboration that includes the Pocky distribution, the open embedded toolchain, and the BitBake compilation engine. This is not an embedded Linux distribution. It builds custom embedded distributions. It's also Python-based, and it relies in a layered architecture of reusable software collection. Each layer contains multiple recipes for building software, and it includes also a graphical user interface in order to make the development easier. Sorry. The key idea I want to introduce you is that by using XDLMake, we can handle the HDL code itself just in the same way that software in order to build a Linux package. If we can fetch the code from a repository, we can configure the code by using XDLMake, and then we can build the whole bit stream by just issuing a make command. So I have built a meta spec layer that is compatible with the Yocto project, so that by including this layer in your own Yocto distribution, you automatically can use the spec board, and the kernel drivers are integrated into the module hierarchy of the Linux image you have created. The user libraries and the tools are ready to be used, and the FPGA bitstream are automatically deployed in place. So I plan to show you. Can I have 1 minute more, please? Yeah, okay. So here I have a little demo of using the Yocto project, the graphical interface of Yocto project, with this layer. Here we can define different layers, and I have added the meta spec layer. So we can choose different pre-built, pre-configured images in order to build the Linux image. We are going to select this one, for example, and now we can edit the recipe. These are already selected by default, the features by default, and if we go to the recipes, we can add the spec-related one, such as the init bit stream, the library, the software, and even an extra one that is the White Rabbit NIC. That is an advanced feature of the spec board that is used in experimental physics facilities. So, and now with this I am going to end very fast. Let's go to the conclusion. As a general remark, XDLMake is a very stable, well-baked, and proved on the field tool. So it's a very useful one. LibreFDA tool is a volunteer effort, so if any of you can help, it's welcome. And the last topic I have introduced you is that we can handle gateware and software as a whole. And I personally believe that by doing this, we can, is one of the only ways of assure that you can reproduce a product in the future, an embedded product, and warrant some quality in a production grade sense. So, simply, as a note, if you have really noticed that, Python is the common language for all the 3 tools that I have introduced you. And finally, if you want to get more information, get involved in the projects, just you can visit the Open Hardware repository and the XDLMake project, and so on. Sorry. Okay.
Time for one question?
Yeah. No, not really. Nowadays, it supports the actual version, the version that is being released just now. It supports all the version. It's based in TCL. It has a TCL backend, and it supports the most of the IC ESC version.
Okay, thank you, Javier.